All right, last little bit. This section is not going to be as long as the previous section. This was just the most logical place to break the chapter. As I mentioned, we will take breaks periodically in class. I know 2.5 hours is a long amount of time to sit. It's a long amount of time to talk. So we will have breaks scattered throughout. So we're going to pick up here talking about leukocytes. These are our white blood cells. These are what are called complete cells. They have a nucleus, they have DNA, they have organelles. They are the only one of the formed elements, erythrocytes, platelets, and leukocytes, that are complete. So erythrocytes and platelets are what are known as incomplete cells. They lack a nucleus and organelles. And we don't have a lot of them. This is less than 1% of our total blood volume, but we know that the number of white blood cells of leukocytes can vary if you're sick. One of the things, you go to the emergency room, you have a fever, you have this unknown illness, they'll often take a blood sample, and they're going to look at things like how many erythrocytes do you have, how many white blood cells do you have, and we know that that number can elevate. Now, white blood cells are capable of doing something that not many other cells are capable of, and that's this thing called diapedesis. And what that means is a white blood cell is capable of leaving the bloodstream and moving into a tissue. So for example, if you cut yourself, or you have a burn, or any other kind of breach of your skin, often bacteria or viruses or other pathogens are introduced into that tissue. And so white blood cells are going to want to move to where those bad pathogens are, rather than waiting for the pathogens to get into the bloodstream. We'll talk more about how diapedesis works here in just a little bit. And you can see here the breakdown of our different types of white blood cells. There are 5 different white blood cells. We can break them into 2 major categories. Those are granulocytes and agranulocytes. And then you can see the individual types here. Now, one great acronym, I'm a big fan of acronyms or mnemonic devices or things that help me to remember lists of things. And one great mnemonic device that can help you remember the different types of white blood cells in order from most to least abundant. So notice here we have neutrophils, we have lymphocytes, monocytes, eosinophils, and basophils. And the acronym that often gets used is never let monkeys eat bananas. So that would tell you the white blood cells in order of abundance. And then if you wanted to remember your granulocytes, you could just remember never eat bananas. So we're going to walk through each one of these. We're actually going to be looking at these in lab on Tuesday, so you'll get a much better visual representation of them in there. We're just going to talk about some of the basic characteristics now. In general, granulocytes tend to be round, and white blood cells overall are way bigger than red blood cells are. That's what you're seeing here. All these small pink ones, these are red blood cells, and you can see the white blood cells here. Lots bigger. And they do have a nucleus. All white blood cells are going to have a nucleus. And one of the big ways you can identify them is the shape of that nucleus. So in our granulocytes, we're going to have what are called lobed nuclei. So you can see instead of having a round cell with a round nucleus, we've got kind of these lobe-shaped structures as our nucleus. I know this is kind of a strange descriptor, and I think it's easier to understand when you see them under the microscope, but granulocytes look grainy, and it's most abundant or most obvious here in the basophil, but you'll see the big difference between the granulocyte and the agranulocyte. All 3 of these, neutrophils, never, eosinophils, eat, basophils, bananas, are all capable of phagocytizing a foreign pathogen. So neutrophils are the most abundant. They are the never of our never let monkeys eat bananas. And they kill bacteria by something called respiratory burst. And the cool thing is they are actually chemically attracted to the site of an infection. We're going to spend a lot of time in the immune system chapter talking about how do white blood cells know where the infection is, and it's almost like they follow this little trail of chemical breadcrumbs to get there. Our eosinophils, I think these are so fascinating, and maybe that's because I think parasites are really cool. Their target is parasitic worms. So this right here is a parasitic worm, and you can see that these small structures surrounding it are our eosinophils. And what they do is they gather around that parasitic worm and they release enzymes that actually dissolve the parasite. You honestly do not get much more metal or badass than that. So they have a very, very specific target. And that's one important thing to note about white blood cells is what their target is. Our neutrophil's target was bacteria. Our eosinophil's target was parasitic worms. And our basophil, this one's really interesting. It's very rare. And it's got a lot going on in it. It looks like there's lots of these granules in it. And these granules contain a chemical substance called histamine. And you've probably heard of histamine before because if you're like me and you have really terrible allergies, you probably take something called an antihistamine. Histamine is one of those chemical breadcrumbs I mentioned on the last slide. So histamine is a chemical substance that will get released and it will attract other white blood cells to an area. Now, for those of us that have allergies, we tend to overproduce a little bit of histamine and it causes a lot of inflammation. We'll talk about its role in inflammation later. You'll get a lot of inflammation in your sinuses and your ears and you feel congested and kind of gross. So the basophil itself is not actually going to attack anything. It's going to release this chemical signal to attract the others that can come and attack a pathogen. Now our A granulocytes, those are these two right here. They include our lymphocytes and monocytes, the let and monkeys of that acrostic. Lymphocytes, these are, I think, by far the easiest to identify when you're looking under a microscope because you have this really big cell with this really big, almost round nucleus that takes up almost the entire thing. Once you see one under a microscope, it's super easy to identify. Now, we don't have a lot of these actually circulating in our blood. These tend to hang out places like our lymph nodes and our tonsils. Those are what are called lymphoid tissues. You do have some in your blood, just not a ton. And there's actually two different kinds of lymphocytes. There are what are called T lymphocytes. Those are going to mature in your thymus gland, which is right here above your heart. Their target is viruses and tumors. And then your B lymphocytes, those are going to mature in your bone marrow. They're going to produce cells that make antibodies. Now, we'll spend a whole chapter talking about the immune system later, but a really common misconception is that antibodies destroy viruses or bacteria. They actually don't. They just mark them so something else can destroy them. It's kind of like they put a hit out on something else so, somebody can come along and kill it. The monocyte is by far the biggest one. This is the one that we see doing diapedesis the most. It leaves the blood and enters the tissues. And once it's entered the tissues, we would refer to it as a macrophage. And the analogy I use with a monocyte is it's a lot like a Superman Clark Kent scenario. So when it's in the blood, we refer to it as a monocyte. It's like Clark Kent, your mild-mannered reporter, glasses, suit, briefcase, going to work at the Daily Planet. But as soon as it senses trouble, it will leave the bloodstream via diapedesis and move into the tissues, and then we would call it Superman. So it's like it's gone in the phone booth, it's done the quick change, it's put its underwear on over its tights, and it's moved out into the tissues, and then we would call it a macrophage. So just like Clark Kent and Superman are the same person, a monocyte and a macrophage are the same cell. They're just going to look a little different, and they're going to work in a slightly different location. And it has a pretty broad range of targets: viruses, bacterial parasites, chronic infections. And if you remember, that's the cell that actually helped us to destroy worn out erythrocytes. So it plays a lot of roles. So leukocytes, I know this looks scary, don't be scared. Leukocytes are formed in a pretty similar fashion to the way erythrocytes are, but one major difference is, remember, leukocytes are complete cells. They keep their nucleus, they keep their organelles, but they do, and I know it's very hard to see, but if you look at the tippy top of that figure, they start as hematopoietic stem cells, just like an erythrocyte does. Now, once they take the step to become a committed cell, there is no turning back. And again, you do not have to know all the intermediate names of these white blood cells here, but you'll notice we have our eosinophils, our basophils, and our neutrophils, and our monocytes right here, and then we have our lymphocytes over here. Lymphocytes are a little bit of a different beast. They do follow a slightly different developmental pathway than the other cells do, but they all retain a nucleus, they all retain their organelles. Now the last formed element we have to talk about are platelets. Platelets are not actually cells. Platelets are actually fragments of these really large cells called megakaryocytes. So what you're looking at here on the screen, and I know it's kind of hard to see the contrast, but you'll have your notes available to look at here. We see all these erythrocytes. We see 4 different white blood cells on this picture. And up here we see this little cluster of platelets. Platelets are very small, and we need them for blood clotting. They do not last long at all. They are the most short-lived of all of the formed elements. They only live for about 10 days. And their formation is also regulated by a hormone. It's a hormone called thrombopoietin. Now, I didn't mention anything about what stimulates white blood cell formation. We'll talk a little bit more about that in the immune system, but one of the big things with white blood cells is they're going to increase in number if there's some sort of infection. So rather than being controlled by a hormone, they're more controlled by the chemical signals that come from infection, whereas erythrocytes and platelets are controlled by a hormone. So here's our hematopoietic stem cell, just like the other two. We go through this developmental pathway, and notice we have this giant cell called a megakaryote. And what it does is it starts to break into these tiny pieces that we know as platelets. Right? That megakaryocyte is really large, it has lots of nuclei, and then it will start to break down into these little tiny platelets. So what happens if you have damage to a blood vessel, right? Some people will refer to it as blood halting or blood clotting. Anytime a blood vessel wall breaks, this process is going to happen. Now that does not mean you are bleeding externally. It could be, I could get a cut on my finger and be bleeding externally, but this damage could occur internally as well. And the second bullet's really important. Blood halting, blood clotting, it's very fast, but it's also very, very localized. We know that blood clots where we don't need them and when we don't need them are incredibly dangerous. And so this process is really, really controlled to make sure it's only happening in the place we need it. And this is one of very few places in the body that we actually see a positive feedback response. So in positive feedback, remember, if you're out of homeostasis, what's going to occur is the response is actually going to get bigger and bigger and bigger and bigger and bigger. A great example of this is childbirth. We know that contractions start out small, they start out further apart, and then they'll get larger and closer together due to the release of the hormone oxytocin. So notice what's happening here, and I know it's a little hard to see, but I've got a break to my blood vessel. The very first thing that's going to happen is that blood vessel is going to constrict. And that's going to help reduce the amount of blood flowing through that, right? If you've sprung a leak in your hose and water is a really precious commodity, you're going to turn the flow of water down so you don't lose this precious resource. Now, unfortunately, we can't turn the flow off, but we can at least turn it down. So the next thing that's going to happen is we're going to start to get platelets sticking to the damaged area. And the reason they can do that is because collagen fibers have become exposed. And so the platelets can stick to that little area of collagen. And I don't know if any of you guys, we used to play this game when I was a kid called Sardines. It was kind of the reverse of hide and go seek. So in hide and go seek, you've got this one person that's hiding and everybody's trying to find them. And they go, oh, found you, found you. In Sardines, what happens is you send a person to hide, and when you find that person, you hide with them. And the next person finds you and they hide with them. So next thing you know, you've got, 10 people crammed in this really tiny space trying to hide from the last person to find them. And then they find them and you yell, sardines! We didn't have cable when I was a kid. We entertained ourselves however we could. So that's what's happening. When one platelet sticks, that tends to attract more platelets to stick because they're releasing these chemicals. Now, what these platelets wind up accomplishing is forming this little plug in the break. Right, so they're forming this little plug, and then we have this substance called fibrin that comes and kind of lays over the top, almost like a little mesh net holding everything in place to form the clot. Now, I mentioned before, don't freak out about this picture. It is just up here to show you exactly how complicated this process is. Blood clotting is one of the most complex processes in the body because you'll notice there's all these different steps that have to occur. And there's lots of different substances called clotting factors that we need for each of the steps to occur. And the really tricky part about this is if you mess up a step or you're missing a clotting factor, you're not going to get successful blood clotting. So most of the clotting factors are actually made in the liver. And you've probably heard of hemophilia before, bleeder's disease. Hemophilia, there's a couple of different forms of it, is a genetic condition, usually a recessive genetic condition, which means you have to get a recessive gene from each parent in order to have it. And what usually is happening with hemophilia is you're unable to make one of the necessary clotting factors that you need. If you've taken history anytime in high school or in college, you probably learned that hemophilia was a common disorder in some royal families because they were often very inbred. A royal had to marry a royal, so they would marry first cousins and things like that. So you started to see more of those recessive disorders coming out. Now, interestingly, vitamin K is a substance that is needed to make 3 of the clotting factors that we make. And vitamin K is something we have to get from our diet. It's not something we can produce internally. So interestingly, and if any of you have had a child recently, you probably know this, but often when babies are born, they're often vitamin K deficient. And so they'll ask for permission to give the baby a vitamin K injection in order to ensure that they can make the clotting factors. Plot twist is because the anti-vaccination movement has become a lot more common recently, you have more parents actually starting to decline the vitamin K injection. Now, the vitamin K injection is not a vaccine. It's literally just a vitamin shot. If you've ever had B12 shots, it's just like that. But a lot of misinformation has gone on, and so there have been cases of babies bleeding to death in the first couple of days after their birth. And if you think about it, you probably don't remember, birth is a pretty traumatic experience. Whether it's a vaginal birth or a C-section, babies are going through a lot. There's a lot of banging around, there's a lot of bruising that can occur. And so we have had cases of babies bleeding to death because their parents have refused the vitamin K shot that's necessary for clotting factors. Now, another interesting thing about clotting factors is we probably all had blood drawn before at the doctor's office. Some of you may have donated blood before, but you can also donate plasma. It's a pretty cool thing, at least the way they used to do it. I don't know if they do it the same way anymore. They'll actually take whole blood out, right? So just the same way that they put in your arm to do a blood donation, they'll take whole blood out, separate the blood, keep the plasma, and put your cells back, so you have like an out and an in going on. And the cool thing about the plasma is where the clotting factors are located. So that's something that an individual with hemophilia will often get transfusions of, either whole blood if they've had a bleeding incident, or they'll get periodic transfusions of plasma because that plasma contains the necessary clotting factors that they would need in order for their blood to clot. So, on that note, a couple of things. We have just finished all of chapter 17. It went fast because I'm not used to talking to an empty classroom. In fact, I feel a little bit silly right now. Usually there's a lot of discussion, there's a lot of questions that happen during lecture. When you get to class tomorrow, so that would be on Tuesday, there will be some questions that we will do in class. If you've already got your top hat set up, that's great. If you don't, that's fine. You're not required to have your top hat set up until Wednesday, but we will do some of those top hat questions so you can get a feel for them. We'll also go back over any expectations. So if there's anything from the syllabus that you had a question about, that you needed some clarification on, please feel free to ask me about that. And also, I emailed you a lot of stuff, but by Monday, the 22nd, the Georgia View should be visible to you, and all the material for the class should be uploaded. So if you have any issues accessing Georgia View or find any material that's missing, please let me know. And I will see your bright, smiling faces at bright and early 8 a.m. on Tuesday morning.